Then
maybe
let me introduce the second speaker, who is Lucia de Luca from Rome, who is going to talk about minimization of fractional seminorms on the real line and applications to misfit dislocations.
Okay, so thanks for the introduction. Thanks to Alicia, Roberta, Matteo, and Giovanni for the organization of this so nice conference, and also for having invited me. So I will talk about what's written in the title, as expected. And so I will talk about minimization of fractional seminorms, gradient flows associated to fractional seminorms on the real line, and applications to misfit dislocations. And the results I will present are obtained, are contained essentially in two papers, one in collaboration with Marcello Ponziglione and Emanuele Spadaro from Rome, and the other one in a preprint together with Michael Goldman and Marcello Ponziglione. Okay, so as customary in applied math talks, I will start from the application, and then I will explain you what is the mathematical problem we want to study. So the picture one should have in mind is the following. So it goes back to 1950. That was the same period of Reed-Shockley law, where people were interested in studying these locations at interfaces. And so the paper, the applied math paper I want to consider is the paper by Mander Merv, where the author is interested in computing the elastic energy and all the other material physical quantities that are the stress and strain induced by a configuration of misfit dislocations. Okay, so now this is the picture. So the idea is that I have two pieces of lattices. So these are the same lattice with with the same orientation, but with a slightly different lattice spacing. And the lattice spacing are C+ for the top lattice and C- for the bottom one. And then I want to compute the energy that is created at interfaces between these two lattices. Okay, so, so the first observation is that it's not convenient to have only elastic deformation at the interface. And this is not energetically convenient, where the energy at this stage of my talk will be the length of these dashed lines. Okay, as you see, after a while, although the difference between the two lattice spacing is very small, after a while I arrive with a very long elastic deformation. So the idea is that so I should not use only elastic deformation, but also plastic ones. And the plastic ones are represented in this region, somehow in this picture here. And okay, so elastic deformation for me in this talk will mean that I have a certain number of particles on the top that connect to the same number of particles on the bottom. So it's this kind of configuration here, okay? And so in these regions that we'll call exactly elastic region, I expect that somehow the horizontal bonds that are on the bottom somehow are shortening, where the horizontal bonds that are on the top are stretching, okay? Then, okay, so as I told you, it's not convenient to have only deformation of this type, but it's convenient to have also plastic deformations. What does this mean? Is that I have a certain number of particles on the top, 3 in this case, that connected to 2 particles on the bottom. So in this case, what I observe is that the horizontal bonds on the top try to be short, and whereas the only bond that is on the bottom try to be long. Okay? So what van der Merwe said in his paper is that if I have a misfit between these two lattices, it's convenient to have an alternation between elastic and plastic parts, and that this alternation is periodic. Okay, so this is somehow the starting point of the computation in this paper. So now so the goal of my talk would be to say, okay, so it's true. So it's true that I have a periodic configuration of this type, so a periodic alternation between elastic and plastic part. And actually, so what I want to say is the fact that it's convenient to put dislocations when one has a model of this type had been proven within somehow semi-continuous model by Muller and Palombaro in the context of nanowires, and then generalized to the purely discrete model for the same problem by Lazzaroni, Palombaro, Schlemmer-Kemper. So in my talk, so the goal of my talk will be to prove that under suitable assumptions, I will have an alternation between elastic and plastic part, and that this alternation is periodic. Okay, and so as Sergio was saying, so someone was mentioning, so this problem has some relation with the so-called Ritz-Shockley formula for grain boundaries. So in that case, the situation is a bit different, because in that case I have two lattices, so the same lattice, one rotated with respect to the other one, and this creates somehow an interface between these two lattices, and along this interface I have a periodic distribution of dislocations. Okay, so this was a computation done in the same spirit of that of van der Merwe, but with for this slightly different problem. And then somehow in the last years, so Lauteri and Lucaus for in the context of minimization, and Fortuna, Garroni, and Spadaro in the context of almost minimizer, so through the rigorous formalism of gamma convergence, had proven somehow that rigorously proven that this the energy that it creates at the interface under suitable energy regimes is compatible with having this periodic distribution of edge dislocations. Okay, so from now on, so as I told you, the plan of my talk will be to prove that the dislocations that are dislocation cores for me are these plastic regions. Will be to prove that these locations are uniformly distributed. And in order to do so, I need to introduce my model. And so now I have to bother you with 3 slides where I have all the rigidity assumptions on my model that will allow me to prove this periodicity. Okay? So for those of you who are not interested in material science, you can skip these 3 slides. Okay. So first slide is about elasticity. Okay, so as in the previous slide, so in the picture, I have 2 lattices that are H plus and H minus, so these are half spaces. And I assume that in these 2 lattices, so I have an isotropic elastic response. So given a certain displacement, capital V, the energy is expressed in terms of, it depends on the symmetric part of the gradients, that is this EV, and it depends on these material constants that are the shear modulus G and the Poisson ratio nu. Okay, so this is the energy of a displacement in R2. But now I'm interested in the interface. So I wanted to see somehow an energy that depends on the trace of this capital V. And now let me note by small v, the trace of capital V along the interface H naught. That is the real line. Okay? So the energy function, the total energy that depends on these traces V plus and V minus, is given by the sum of these elastic energies that are the ones that are on the top. And okay, so the energies that depends on the trace are obtained by minimizing among the displacements capital V in R2 the energy that I written on the first formula. And now, using a Dirichlet-Neumann map, one can show that this minimization gives back an energy that depends on the trace, small v, okay? And this is actually the fractional Gagliardo seminorm with power 1/2. Let me stress the fact that there is a difference between the first formula and the last one, because in the first formula, I consider the integral over the whole H plus, that is, or H minus, that is R times either R plus or R minus. But as I told you, I wanted to see periodic trace. So I wanted to have an energy, so if I compute the energy on the whole R, we'd have an infinite energy. So this is the reason why I put myself on a large box that is 0 capital L. I assume that V is capital L periodic. And okay, well, I assume that L is larger and larger than the periodicity scale that I want to see. And then instead of considering somehow the infinite fractional Gagliardo seminorm, I consider a kind of density of the Gagliardo seminorm that depends on this length L. Okay, so in this slide, I have only elasticity. And this is just to say that the energy I want to look at is the fractional Gagliardo seminorm of the trace. Now I have to relate these 2 traces that are V plus and V minus, and that should, I have to relate these traces with the misfit that I have between the 2 lattices. And now I start with the assumption on the model I will consider, so the assumptions on V. So as I told you, H naught, that is the interfaces, is divided into 2 parts that are an elastic part and a plastic part. Okay, so recall me that the C plus and C minus are the lattice spacing, and that the bottom lattice spacing is larger than the top one. And I will work within the limit of semi-coherent interface. That means that the C plus is very close to C minus. Okay, and they are very close to a certain intermediate lattice spacing C that is equal to the average. Okay, so first assumption that I have is, first rigidity assumption, is that the derivative of the traces are constant in the elastic part and constant in the plastic part. And I will denote by ME, plus or minus, and MP, these derivatives. Now, let me say once again what I said when I did the picture, when I presented you the picture. So I have a perfect match in the elastic part. The same number of particles on the top connected to the same number of particles on the bottom. So this means that this equality holds true. So if one writes down, so this is essentially the identity plus the displacement times C plus, the identity times the displacement plus times C minus. And by linearizing around the condition that C plus is very close to C minus, one ends up with the fact that the difference between the two elastic slopes, M plus and M minus, is equal to the difference between the two lattice spacings divided by C, but somehow these spacings are very close to each other, so I call this distance, this difference M, and M is small. But now I can I can assume all the elastic coefficients in terms of a certain parameter alpha elastic, and I have that the elastic coefficient on the top part is equal to alpha E times M, and the elastic coefficient is equal to minus M times 1 minus alpha, so that I have that this relation, I can enforce this relation here. But the only thing that one should remember about this, should recall, is that the difference between the two elastic slopes is small. Now I do the same thing in the plastic part, but remembering that in this case, I have not the same number of particles that connect on the top and on the bottom. And here, actually, I can take whatever, but I say, as before, 2 particles on the bottom that connect to the 3 particles on the top. And now I enforce the same, so I do exactly the same argument, and I enforcing the same condition that I have here and linearizing around the fact that the C plus and C minus are close to each other. I have that the difference between the plastic slopes is equal to a certain number that is negative, that depends on this parameter alpha p. But the important thing is that this difference is close to -1. So this means that I have, when looking somehow the difference of the slopes, I can have only 2 choices. So one is the positive one that is small, and then the negative one that is close to -1. Okay? So this is the rigidity assumption, and now I come with the most important rigidity assumption in my talk, and namely that the plastic region is quantized. So the plastic region cannot be whatever. I assume that the plastic regions that are what I before called the dislocation course is given by union of epsilon intervals. So epsilon means the size of the core, and this epsilon is somehow a multiple of C. Okay, this is something that is quite reasonable in material science because somehow everybody knows that the core is quantized, but from a mathematical point of view is a very strong assumption. That there was not. So, so no, this is enters only as a constraint. So in the energy, so the energy is just the elastic energy. Then at a certain point, that is next slide, no, but I see, yeah. So exactly. So okay, thanks for the question, because so this is the setting for the energy, and now I'm putting all the assumptions in the class of functions that I want to minimize. Okay, and then exactly this is what I want to say. Now I consider I denote by V the difference between V plus and V minus between the traces, and so somehow this V is measuring the constraint. I do some scaling for essentially psychological reasons. I want to work with the positive derivative that is 1 and the negative derivative that is large. Okay, so I call 1 and minus capital lambda, and capital lambda is 1 over m, where m is assumed to be small. And then, so now the relevant variable will be u. By the quantization assumption, as I told you before, that the region where u prime is negative is given by union of epsilon intervals. And now I'm forcing another term, namely that the distribution parameters alpha elastic and alpha plastic are all equal. I have that v plus and v minus can be all written in terms of alpha and v, okay, where v is their difference. So the energy before was ds1, but now I can rewrite v plus as alpha v, and v minus as 1 minus alpha v, then everything is a function of u, and then what I end up with is this formula. So I have constants depending on alpha, that can be somehow, in order to minimize this energy, I have to minimize every term. So this term depends on alpha and can be minimized in a very easy way. And then I have to minimize this term. That is the difficult part. So now this is the energy I want to consider, and then I come to the mathematics. Okay, so until now I told you that I have the fractional Gagliardo seminorm with power 1 half, because this is the one coming from the problem. But what I will say will hold true for any s in between 0 and 1. So I will work with that. So let me put here in order to see the time. So let us consider s in between 0 and 1. Let me denote by lambda and 1 these the slopes for the function u. Okay, so I want to see something that is periodic. And so I put myself in the case that capital L is the periodicity that I'm assuming a priori is given by a multiple of the period that I want to see. And my goal is to minimize this energy, that is the fractional Gagliardo seminorm in terms of a density, in this set here. So the set of the functions that are piecewise affine, capital L periodic, that can have only 2 slopes, and for which the negative slope, the region of the negative slope is quantized by epsilon. Okay, and now the result I will prove, okay, now it's clear, because it depends on the assumptions, is that the unique minimizer of this energy in this class here is given by the minimal periodic function that I can construct. And it is this function u bar. Okay, so the minimizer is unique up to translations that are both horizontal and vertical, because the energy is insensitive to this kind of translations. And okay, so this result proves that I have a periodic core, dislocation cores, because as you see, the dislocation scores are these epsilon here that are periodically distributed with a minimal period that is somehow, in a certain sense, 1. Okay, now the reason why I told you the assumptions and I try to convince you that these assumptions are somehow reasonable is that I wanted to prove this theorem. Okay, so I wanted to give a proof of this result, and the proof of this result somehow is quite simple, because it's in a certain sense standard. So it consists in computing the first variation, and the first variation of the Gagliardo seminorm is the fractional Laplacian, and then to use the maximum principle for the fractional Laplacian. Okay, so let me see how it works. So let U be a minimizer of the energy. And then, okay, as I told you, the first variation of the fractional Gagliardo seminorm is the fractional Laplacian that is defined by this formula here. So here I'm not saying so it's the average actually of the fractional Laplacian. So here I'm not saying the variation that I want to do. So the variation I'm considering of this type. So I put myself in a certain minimizer, and the local minimizer of the function u is at the extreme point of a certain dislocation core. That is something that I want to move. And starting from u, I add the characteristic function of an interval that is close to this point x0. Okay, and then when I do, so if I am in the case of an isolated singularity, I can do this variation both adding or so if I were in this case, where I have a single dislocation, so I can both add and subtract these characteristic functions. I'm going both directions. But if I am in a situation of multiple dislocation, I can do variation only in one sense. So this is the reason why if I am in a local minimizer here, the only thing that I can prove is that if u is a minimizer, then the integral over this core here of the fractional Laplacian is positive. Okay, and now what I do is to consider a global minimizer of the energy and to consider the function, the candidate minimizer, that for which this point is a local and a global minimizer of the function. So I somehow attaching to this graph here the graph of the candidate minimizer. So in view of the quantization assumption, I have that these two functions, so this is the one that I expect to be the minimizer, coincides with u in this interval here. But so if you look at the shape of the fractional Laplacian, I have that u coincides with v here. And now the most important fact is that v, so the function I just constructed, is below u in R. And this is due to the fact that I have the quantization assumption. Okay, because if I were able to find a point where u is below v, then in view of the quantization assumption, I would be able to find another point for which the value of u is below x naught. But I assume that x naught is a global minimizer of the energy. Okay, so now if you look at the shape of the fractional Laplacian, I have that u coincides with v, and that u is above v everywhere in R. So I'm able to prove that I just proved that the average of v, of the fractional Laplacian of v, is above the average of the fractional Laplacian of u. But by symmetry reasons, this average is equal to 0. So I have that this chain of inequalities is actually a chain of equalities, and that v should coincide with u. So I have that I just proven that the only minimizer of the energy in this class is given by this function u bar here. Okay, so this is our proof. And now before going on with our results, let me relate the result I just proven with the standard results on the minimization of norms on the norms on the real line and that exhibit periodic minimizers. So first thing is some of the oldest thing in this direction is the paper by Müller. Sorry. So in this case, the author consider, so as in our case, the author have considered piecewise affine periodic functions that whose distributional derivative is given either to +1 or -1. Okay, so in this case, the wells are equally modulus. And the energy that Müller wants to minimize, okay, it's not exactly this one, but this is some of the closest to our case, is the square del2 norm plus a penalization on this on the oscillation of the function that is given by delta, the cardinality of the jump set of u prime. Okay, and so what Müller proved is that minimizers of this energy in this class here are periodic with a scale that depends on this delta here, and the scale, the power is 1/3. And the proof of this result works like that. So taking a function u that is in this set here, let me denote by x1 extended jump points of this of the first derivative of u. And okay, so by the periodicity assumption, this the number of these jump points should be even. Okay, and then I can rewrite the energy in this term. So the energy can be rewritten as the sum of the squared L2 norms of the function u computed between in an interval with extreme points to consecutive jump points. Okay, so this is just rewriting of this. And here I have the cardinality of the jump set of u prime that is equal to 2 times n. And now what I observe is that in this interval here, so these are 2 consecutive jump points of u prime, I have that equal u prime is equal to 1 or u prime is equal to -1. So I can minimize this energy. Okay, and when I minimize this energy, I have something that depends only on the length of this interval here. Okay, so this is a kind of zero calculus computation. And then what I notice that this function is convex, so I can use Jensen inequality and to show that the term of the right-hand side has this behavior here. And now this right-hand side is minimized when these two addenda are of the same order, namely when n is of the form delta to the power minus 1 over 3. Okay, so this computation here is somehow instrumental to Müller to prove a much more difficult result, namely when the cardinality of the jump set of U prime is replaced by its phase field approximation. And that is the modica mortola functional. Okay, so the same, so this periodicity result holds true for delta small, also if I do not have the sharp interface here. And in some of these cases, it's much more complicated, no? Because we have the scale of modica mortola that is of order delta, and the periodicity scale that is of the power of order delta to the power 1 over 3, and one should prove that these scales do not affect each other. And okay, so this computation I've shown you easily uses the fact that the two wells are symmetric, so I have the same modulus, and ran away extended the result by Müller, proving that it also for non-symmetric wells. Okay, so this is the first result, but actually so this is close to our because they have periodicity of minimizers, but the norm that the bulk energy that Müller is considering is the square del 2 norm that is local, whereas in our case, we have a non-local energy that is the fractional Gallardo seminorm. And this was done also by Müller and Giuliani in 2011. So in this case, the idea was to minimize exactly the energy that I had before with this condition of symmetric wells, and where the bulk energy is the 1/2 Gallardo seminorm. Okay, and also in this case, Giuliani and Müller proved that minimizers are periodic with a scale that is dictated by this delta, but has a different power. And I show you the proof of this case. Sorry, an idea of the proof, clearly. So in this case, the proof works like that. So first of all, one can rewrite the interaction kernel, that is the t to the power minus over 2, as this integral here. Okay, and so instead of proving the periodicity directly for this functional here, one prove it for the functional where the interaction kernel is exponential, but depends linearly on the distance between the points x and y. Now, so the idea is that if I'm able to prove the periodicity for these functionals here, then I'm done. And so what is difficult in this? So in this case, one would like to replicate the computation that one had before, and especially the first one. So the one for which I'm able to compare the energy, so to minimize the energy on each interval between two jump points. But in this case, sorry, in the L2 case, this energy was local, and in this case, the energy is not local, okay, because I have a double integral. And so in order to do this, one cannot, restrict to the only interval between two jump points, has to construct the function also on the wall R. And the way of constructing the function on the real line is the so-called the reflection positivity. So the idea is that I have a function that has a certain slope, say 1, in between two jump points, and I reflect this function in all the other intervals in a periodic way. When reflecting the functionals, the function, I have a function with a slope that was 1, and when I'm reflecting it, I have a function with slope -1. So I do not quit the constraint. So during this reflection positivity argument, then one is able to do the first inequality that Müller had before, and then to do all the other computations. But as you see, the reflection positivity uses the fact that the wells are symmetric. So in our case, where we don't have in principle wells that are not symmetric, we cannot use this technique. Okay, and let me say once again that this was not the main result of this paper by Giuliani and Müller, but somehow they were interested to look at the problem in higher dimension, and previous computation in this direction will be done by Sergio Conti in this paper. Okay, so this is just summarized in literature was as follows. So the authors consider functionals of this type a bulk energy depending on U plus a penalization terms on the oscillations among functions U that have two slopes, +1 and -1. So as for S equal to 1/2, we have the paper by Giuliani and Müller that says that the minimizers are delta to the power 1/2 periodic. As for S equal to 0, that corresponds to the L2 norm. Minimizers are delta to the power 1/3 periodic. For S in between 0 and 1, what we expect is to have another scale that depends on delta through S. And what's the relation with our paper is that our paper is easier. Okay, so we do not have this assumption in the symmetric wells, but we have that all the scales above are epsilon in view of the quantization assumption. So we do not have an intrinsic scale like in this paper that determines somehow the periodicity of the minimizers, but we impose it. Okay, so this is somehow the relation with the pre-existing literature. And now let me speak in the rest of my talk of what we did together with Michael. So until now, we have considered the fractional Gagliardo seminorm of this type, and we have minimized them in this class here. Okay, but so the first question is, what happens if instead of taking a lambda that is a certain number that I imagine to be big, I take lambda equal to plus infinity. So this means that instead of having very negative slope, I'm having a vertical slope. So, and this means that my dislocation course, what I call the plastic region, are becoming points. So I have somehow point singularities. And so these are, in this case, I have that the function u that I'm defining here is jumping along this, in this point. Okay, so this is what we did. And how does the quantization assumption work in this case? Yeah, in this case, I have that the distributional derivative now is equal to 1 and minus infinity. And minus infinity is, means that I have a sum of Dirac deltas. And the quantization assumption is telling me that these Dirac deltas should have positive integer weight. Okay, so now I want to consider this problem here with this condition, with lambda equal to plus infinity, and with this constraint here. Okay, so this can be done when S is in the subcritical case. So the fractional Gagliardo seminorm when S is subcritical is finite. And this kind of limit, say, as epsilon comes to 0, allows me to define the energy, okay, not on the course, but as an energy that depends on these point singularities that are denoted by this capital X. And the energy is defined as the fractional Gagliardo seminorm of the function u of x. That is the function that satisfies this condition. Okay, there are a lot of functions satisfying this condition, but the energy is insensitive to translations. So any function I take, I always have the same energy. Okay, as I told you before, in the subcritical case, I can have a function that jumps because the energy is finite. And what we proved together with Miguel and Marcello is that in this case, critical points of the energies are equispaced. Okay, so I do not have only that there is only one minimizer, but there is only one critical point. And this one critical point is clearly a minimizer, a local minimizer, a global minimizer. Okay, so I showed the proof of this fact because I think it's very nice and it's very easy, I must say. So first thing, okay, it's not convenient to have multiple singularities, okay? Because if I have a multiple singularity, then separating them, I decrease the energy of minus infinity. So from now on, I will focus on regular configurations that are configuration with isolated singularities. Second thing is that when I compute the first variation of the energy, that is the variation that I do when I move the particles, and now I have isolated singularities, so I can move them both in the right and the left direction. The first variation of the energy is the fractional Laplacian. Here I have a function that is jumping, so I have to define what is the value of the function in the jump point, and this is what you expect, namely the average between the positive and negative trace. Okay, so this is the first variation. Now using, so if I have an equispaced configuration, then by symmetry I have that the fractional Laplacians are all equal to 0. Okay, so I have that the equispaced configurations are for sure critical points of the energy. And then I want to prove that the they are the only ones. But if I'm able to prove that the second variation is positive definite, then I'm done, because I have an energy, so I have a parabola, okay? So the second derivative is positive, and I found already a critical point. And okay, there is only one critical point, and this point is local minimizer and global minimizer. And the second variation is has this form, so it can be computed. And these coefficients here are given by this series here that are convergent series, but for the most important fact is that they are positive. And so I'm done. So I have only one critical point. Let me tell you another thing, that if I take this vector h that is in the direction orthogonal to global translations that do not affect the energy, then what we can prove is that the Hessian is bounded from below by a constant that depends on S and capital L times the squared L2 norm. Okay, so this, as you can figure out, this is important for the convergence rate in the dynamics, and that this estimate is sharp. Namely, I cannot do better than this estimate if instead of putting X, I put the equispaced configuration. And now, so this is the dynamical, the result about the dynamics that says that if I start from a regular configuration, then considering the gradient flow of the energy starting from this regular configuration, this gradient flow exists for all times as no collision of particles and converges as time goes to plus infinity to a minimizer, namely to an equispaced configuration. And moreover, in view of the estimate I showed you before, the convergence to the equilibrium is exponentially fast. Namely, that if I denote by x naught, the equispaced configuration that has the same barycenter of x naught, because global translation does not produce, so somehow are completely useless for the dynamics, then I have that the convergence of my solution to this equilibrium is exponentially fast, and the exponent depends on this constant here. Okay, so this is what happens in the subcritical case, but in the previous slide, I told you the important case is S equal to 1/2 that is excluded by the computation that I've done until now. So let me see what happens in the critical and supercritical case. So I want to do the same stuff. I want to have an energy that depends on the particles, and this energy is defined as the fractional Gallardo seminorm of the function u associated to x. But for S in between 1/2 and 1, I have that this energy is plus infinity. So I need to regularize it. So in this case, I cannot do this fact that the chords are becoming points, because the energy is equal to plus infinity for any configuration. And in order to do this, I do a regularization that is slightly different with respect to what we have done with Emanuele. Namely, I define an energy that depends on a certain parameter epsilon, where that is defined as the fractional Gallardo seminorm of the function u regularized with this convolution kernel rho epsilon that is a standard modifier. Okay, so what's the comparison with the paper with Emanuele? So in that case, we had the course, the epsilon course, and we were fixing the profile of this course that were affine. In this case, we say, okay, we do not fix the profile, and we will show that somehow the periodicity and the dynamics is not affected by the shape of this course. So this is a generic modifier, and we will see that the dynamics is not affected by the shape of the profile we are fixing in the course. Okay, so clearly we have the same result as we proven before with Emanuele. So for epsilon small, minimizers of the energy in this class are equispaced and have lattice spacing equal to 1. So in order to prove this result, we argued as in the subcritical case, but here we have somehow we have to take care. So here we are doing an average. Okay, so we are using a modifier, and so we have to ensure ourselves. So when using the procedure that we had before, we have to ensure ourselves that when minimizing, we have not two very close particles. So the first thing that we have to prove. Okay, so this is. Please don't read this lemma. So the idea is that if I have two parties, if I have a minimizer, there is a minimal distance between particles. Okay, and okay, so this is expressed by this lemma here. And then once I'm I've proven this, then the proof of minimality works exactly as in the previous case. So it's enough to reason in the family of configuration whose minimal distance is larger than a certain threshold delta. And then in this case, in this region, we compute the second variation of the energy, and the second variation of this energy in this region is positive. Okay, and although, so the coefficient here depends on epsilon. And okay, so I want to say one thing that is, okay, so these are the coefficients of the second variation, this A epsilon. And let me say that when epsilon tends to 0, this coefficient tends to the coefficients of the form that I had before. That was the convergence series with the power 1 plus 2. So that was 1 over, say, t to the power 1 plus 2s. That converges also for s in between 1 half and 1. And this is telling me one thing, that, okay, it's true. For s larger than 1 half, the energy is plus infinity. The first variation is plus infinity, but the second variation is finite. So, okay, so this was and this is the important part, for instance, to prove the both the minimizer, the uniqueness of the minimizer, but the exponentially fast convergence. And then in this case, we are able to prove the same dynamic result. Okay, so that when for epsilon small enough, depending on x naught, we can find a unique solution that exponentially fast converges to the equilibrium. Okay, so this is these are the results we want to prove. And if I have 5, say. No, in view of this fact here. So you have a good convergence of these coefficients here. So yeah, thanks. Yeah, exactly. So that's the point. Also in the dynamics, you don't see any effect of the regularization, more or less. Okay, so if I have 5 minutes, I would like to tell you about some generalization of these results. So let me start from a soft one. So until now, we have considered the problem, so the fractional Gallardo-Seminar with exponent 2. Now let me say, okay, so what I said you can be generalized to exponent p, with p larger than 1. And this is something that Pini and Santilli, that are 2 PhD students in Rome, have done, proving that the minimizers of this energy are 1 periodic. Okay, so I have exactly the minimal periodicity. And okay, so the only about this, I want to tell you only one thing. So as I told you many times during this talk, so if I did the first variation of the energy, then I say that you naturally end up with the fractional Laplacian, and this is not true. So this is true only for p equal to 2, in the sense that if one does the variations, and now the variations consist in moving the points, okay? And then the first variation of this of the energy for generic p can be written in this way, okay? But this is not the p fractional Laplacian, okay? And the fact that for p equal to 2, one end up with the fractional Laplacian is actually by chance, because when p is equal to 2, here I have the difference of 2 squares, and that is the sum times the difference, and the difference is equal to 1. So, but this is somehow only, this happens only for p. So, and actually this is not, so when one thinks at this problem, this is not surprising, because the variations I'm doing are different. So when I do variation for the energy for the fractional Laplacian, I consider u plus h phi. Whereas in this case, I'm doing u plus the characteristic function of an interval with the size h. So it's clear that the first variation is this one, and has nothing to do with the fractional Laplacian. And so the other thing I want to say is that, okay, so this one can compute the limit also in this periodic setting of these energies, so the fractional Gallardo-Seminars when s goes to 0, and when one ends up with this kind of non-local LP norms. And also the only minima, so the opinions Santilli proved that also for p, for generic p, there is a unique minimizer of the energy, and that is 1 periodic. And in this respect, one somehow could try to generalize also the results by Müller and by Giuliani and Müller to these somehow different norms. So when one considers p different from 2, also in the case of symmetric wells. Okay, so this is more or less the soft generalization. But then someone we noticed that our schema was very robust, no? Because there's nothing more robust than saying first variation 0, second variation positive, I have a minimizer and a critical point. So I say maybe it can be generalized to other non-local functionals, reasonable non-local functionals. And then we started from the Ritz functional. Okay, so in this case, I have a power that is in between 0 and 1, and the interaction kernel is not integrable at plus infinity, but integrable at the origin. Okay, so I define the energy in this way. So as the double integral, okay, one over the interval with length L, and the other one over the real line of the product between the u's times this kernel. And this can be written as the L2 product between U and the Ritz potential. That is K alpha star U, where the K alpha is the this kernel here. So this kernel is in L1 lock. Okay, first thing, I say that this function, I've written that this functional is defined in this space here, so the L periodic function, the L below stay for L periodic, and 0, because one has to ensure that this integral is finite. Okay, I have a periodic functional, and the 0 stays for the fact that you should have 0 average on the interval 0 capital L, because otherwise this integral doesn't converge. Now one has an argument like the Leibniz criterion for series. So this was the interaction energy that we wanted to consider. So why this? Because it's a simple non-local energy, and because when one multiply this energy times alpha, it converges to the square L2 norm. So for the square L2 norm, we know that the minimizers are periodic. We are able to treat the case of other non-local functionals. Maybe the same thing should work. And so we define the energy as before. So as an energy that depends on the position of particles through this formula here, where this function u is the function as before, so satisfy this condition and distributional derivative, and where we have to add the assumption that the average of u is equal to 0 in the interval. But then this condition creates a lot of problem. Okay, because as I told you before, some of the variation that we did were to take the function u and to add the characteristic function. But then this cannot be done anymore because I have to preserve this constraint. And this introduces a lot of errors when doing some of the first variation, the second variation, that some are not, so it's quite difficult to understand what is the sign of the second derivative. Okay, the second variation. And in principle, I can say that in the formula I had here, so when proving the second variation exactly, so I cannot say that all these coefficients are positive. So I do believe that the sum of the second variation is positive, but I'm not able to prove that any single coefficient is positive. And this somehow is kind of a challenging problem for us. And in this respect, so one can look also at the problem for symmetric wells with intrinsic scale delta that has not been done in the literature. And with this, I can stop and thank you for your attention.
Standard, I mean, I guess it's a standard question, but it's also a relevant one. How about 2D and a 3D ambient space?
Okay, so the problem makes sense in 2D and 3D, but we were not able to find a generalization that was so something in between impossible and trivial. So either one. So in the sense that either you have somehow a very rigid assumption that allows to decouple the problem, or you have something where you are not able to manage, to control all the possible pathologic things that you can do. So I don't know what to say, but so the standard idea was to consider so this kind of two derivatives, no? And say, okay, say in the 2D case, you have a function that is that has two components, and then for each of the two components, you have to ensure that you have two slopes, okay? But in this case, so you have u equal to u1, u2. For u1, you have two slopes. For u2, you have two slopes. But if you have an energy, so there is a way of decoupling the energy, and then in this case, you have the sum of these things, and everything behaves independently. Whereas for somehow, if you try to consider an energy that depends on both in a non-trivial way that does not decouple, we were not able to prove somehow to consider anything that was meaningful
So do you then expect, what do you expect?
So okay, that is a good point. So in this case, one expects to have, so the periodicity becomes a net, okay? You have a net of singularities. But then it's not clear. So if this net of singularity is affected by the lattice structure you are considering, so you start from a cubic lattice and you expect a quadratic lattice, a square lattice of singularities, or if something that is independent of that. So if you have that you have like an honeycomb structure that minimizes the perimeter and is not affected by the lattice symmetries that you had before. So that is, I say asked to many people, but there is not a uniquely determined answer, not even in people doing simulations.
Okay, thank you. Are there further questions? Oh, okay. Then let's thank the speaker again.
Thanks.
The first talk of the afternoon will be given by Giulia Bevilacqua from the University of Pisa, and she will be speaking about variational analysis of axisymmetric nematic forms.
Thanks. Thanks for the introduction. And first of all, I would like to thank the organizers, Roberta, Alice, Giovanni, and Matteo, for this opportunity. It's my second talk in the Centro Ennio De Giorgi, and it's I'm a bit nervous, so just to be honest. So today I want to present this result. I hope in the final 10 minutes of my talk to give what we are doing now, but today we start with the paper that is on archive. Is in collaboration with Chiara Lonati and Luca Lussardi. Chiara is a postdoc in Politecnico di Torino, and Luca Lussardi, I think that everybody knows in Politecnico di Torino, and Alfredo Marzocchi was who is in Università Cattolica del Sacro Cuore in Brescia. So let me start from the energy functional that we want to consider. I want to give you motivation that we are interested in such a functional, but just to set the mathematical setting, I want to write the energy functional. The energy functional we consider is of this form, is the integral over S, where S is a surface, and a surface in R3, sorry. So it's a two-dimensional surface in R3. And we want to minimize, we want to study this energy functional. Where here gamma is the surface tension. So it is a constant. Kappa is what we call the nematic constant. And n is the nematic vector. Nematic vector is a unit vector, and it constrains to lie. So for all point x on the surface, it is constrained to lie on the tangent vector. So n belongs to the tangent vector of S. So the picture that we need to have in mind, so we are considering a surface. I don't care about, for a moment, about regularity, assumption on that. So think about a surface, a two-dimensional surface in R3, and we are studying this energy functional, in which there are two constants, surface tension plus the nematic constant, and there is this operator. Which will be clear in a while. So we are penalizing the gradient of n, where n is a nematic vector, which is constrained to lie. This nematic vector is constrained to lie on the tangent vector for each point of the surface. So it's constrained to lie on the tangent space of the surface. Okay. So, this is the energy functional. What are the motivation in studying this energy functional? I think that in that audience and for everybody is immediately clear, because obviously, if we consider k equal to 0 and we just minimize and we want to study this energy functional, this is the classical Plateau problem. So we just minimize the area. If gamma is equal to 0 and S is fixed, so it is okay, it is fixed, and it's not a surface, but it is an entire domain. Now I'm calling omega, sorry. An omega is a regular set. For instance, let's think about RD. This energy functional can be written in a more general form of this type. Is the integral over omega, which is assigned, is regular, and so all hypotheses that you want to consider, of a suitable energy, elastic energy, W, which depends on n and the gradient of n in the entire domain. So this is the classical theory for liquid crystals. And this energy has been studied a lot. Here, for instance, I want to mention people like Fangualin, Virga, and John Ball in the study of and the minimization of this energy functional, providing, for instance, omega to be a regular set and providing existence and regularity for this type of solutions. Obviously, this type of energy can be must be specified, and you must add some hypotheses in order to describe a suitable physical and elastic approximation for liquid crystal. I just want to mention like hypothesis for framing differences, or like n. You can require that there is no polarization for the nematic vector, so you cannot distinguish what is the head, what is the tail of this vector. Okay, so which is the most classical energy that one can study for nematic liquid crystal? It has this form, and now I want to explain. Okay, let me write it before. It is of this form. It is a constant K1 times the divergence of n square plus K2 n dot the curl of n square plus K free, the absolute value of n curl of n square. Where from a physical point of view, this term takes into account, I'm not considering, so I'm in a more general setting in which S is fixed, and I'm just requiring that n is, I'm in the full dimension. So this term reflects what is called in the liquid crystal theory as a splay effect. So how the vector field can be outside the plane. So this reflects on the bend, on the fact that the liquid crystal can bend, so on the effect of bending, and this relies on torsion. Okay, on the torque part. And there is an approximation. This is an exercise. A real exercise. If you take K1 equal to K2 equal to K3, then you can get the Onsen approximation, one constant approximation, and the energy reads as K times the gradient of n, the gradient of n square. Okay, so in some sense, this energy comes from the interplay between area function. The n. Yes, sorry. Yes, I said. I just said I didn't write. Yes, sorry. Okay. No, but thanks for for asking this. Yes, so this energy functional comes from the effect, so the interplay between the area functional together with a part which which comes from the theory of nematic liquid crystal in a suitable approximation. But what you can see is that every time for this energy functional, every time the surface changes, every time the direction of n changes, and vice versa. So every time the nematic vector is aligned, so prefers to align in some direction, every time the surface must be adapted to its direction. So our goal was to study this type of energy functional in which we wanted to take into account, and we want to provide a sort of rigorous derivation of study of minimizer and for this type of energy functional. Okay. So what was known in literature for this type of energy functional? The first result is by Jomi in 2012, in which what he did, okay, he considered a general surface, so it didn't give any any hypothesis, so smooth, but okay, you will understand this sentence in this part of the blackboard. And for the differential operator on the nematic vector, he considered the covariant derivative. So the covariant derivative. And this energy functional can be rewritten in this form. Okay, it's just a simplification to explain his result. Is S, it is gamma 1 plus k divided by 2 divided by gamma. Yes, the covariant derivative of n square. And this quantity, which will appear also during my talk, I will denote with C. So it's nothing but the ratio between the two constants appearing in the problem. And his result, so what he did, he looks for critical points for this type of energy functional, assuming that the differential operator is the covariant derivative. And what he proves is that if this constant C is below a certain threshold, I don't want to be precise on that, and now you will understand why at the end of the talk. He says that the solution, so critical points for this energy functional, are minimal surfaces. If C is greater than C0, then critical points have Gaussian curvature negative. And actually, this result is wrong. So it's not correct, because especially this first part, you will see at the end of my talk that it's not possible that every time you switch on the nematic contribution, a minimal surface E will be a critical point for this energy functional. I will prove that this couldn't appear, okay? So this is the first result that in studying critical points, okay, he didn't derive rigorously a theory about a minimizer for this type of energy functional. He just derived critical points for the energy functional, and he studied and he concluded this type of results. Later on, Napoli and Vergori in 2018, what they did, they considered a specific class of surface, which are revolution surfaces. And now you understand my title, axisymmetric nematic, so axisymmetric in my title, in which you consider a function rho from minus h to h in R, and this revolution surface must are subjected, so let me call this axis x, this distance is 2h, and this is the radius small r, yes, I think so. So they consider a revolution surface with a suitable boundary condition. They require that rho, so the function in plus and minus h, must be equal to r. So such a surface must span these two coaxial rings. So you imagine immediately that if k is equal to 0, and you want to consider that in the class of graph, what you end up in this configuration is or the catenoid or the solution of the two disks. Okay? Okay, but differently, exactly. Yes. But differently, so this is the first hypothesis. The second one, so different from what Jomi did, instead of considering as differential operator the covariant derivative, he considers the surface gradient. the surface gradient of n, which actually is the right operator that one has to consider on a surface, which is nothing but the gradient of n composed with the projection on the surface. And you can write the norm, the square of the norm of this differential operator, it can be written as the sum of the covariant derivative plus what is known as an extrinsic curvature. So in some sense, the covariant derivative, okay, everybody I think that knows, takes care of what happens on the surface. This allows the possibility that the surface can bend, and obviously you have to take into account. Okay, this is the right operator that one has to consider if you consider the you consider a surface, and I want to okay, and in this setting, okay, they make another assumption. They make another assumption, which is the fact that yes, if you call A1 and the A2 an orthonormal basis on S, so you can think that this is the direction on the parallel, and this is the direction on the meridian. You can write n as the cosinus of alpha A1 plus the sinus of alpha E2. Okay? And what they did, and now I wanted to underline this because we can prove, what they did, this is an hypothesis that they made, is that for them, the angle alpha depends just on x, but it can be proved. So now, for now on, I just assume that the angle depends on x, but you can prove that if you put the angle theta, obviously the angle phi, you don't have the dependence because it's of revolution surface, you can remove that. But believe me, I don't want to spend time on that. But so that assumption is not, let's say, so strange, let's say. Okay? So in this setting, the energy functional, so the energy functional is of this form. Okay? So it depends on rho and alpha, because now the times the n, it depends just on an angle, and s depends just on the function rho. So this is equal to, okay, no, minus HH, the area term. Okay, so this is classical. This comes from the area, plus, okay, yes. I put the constant c, which is exactly the ratio between the two constants, and I put outside the integral. It is equal to minus HH, so rho prime square divided by rho square root of 1 plus rho prime square, plus alpha prime square, oops, rho divided by 1 plus rho prime square, plus, there are two other more terms, minus HH, cosinus square of alpha divided by rho, the square root of 1 plus rho prime square, plus rho second derivative, rho sinus square alpha divided by 1 plus rho prime square in x. Okay? And actually, okay, this comes from the area. This first line comes from the covariant derivative. And the last part comes from the extrinsic curvature. Okay? And this can be derived in an easy way. Okay? Good. Okay? So, what they did, okay? What Napoli and Vergori did, they studied the critical points for this energy functional, so they derive Euler-Lagrange equation, and they solve them numerically. And the results, in my honest opinion, are quite interesting, because what they did in solving numerically the Euler-Lagrange equation, they fix a value of the angle. For instance, alpha equal to pi over 2. So this means that we are requiring that the nematic vector is aligned along the meridians, and the solution looks like that. So for c equal to 0, you get exactly the catenoid. Okay? And this is expected because you're just considering the area. So for c greater than 0, so positive, the solution, so imagine that this is the catenoid, looks like that. Oops, sorry, here. So this is the solution for c equal to 0. So let's say is a fatter catenoid. And for c equal to plus infinity, you get the cylinder. So in some sense, every time you switch on the nematic contribution, you get a different behavior of the solution that you can realize, you can connect with respect to the case c equal to 0. So in the case where the nematic is not present, they make another study, which is the case of alpha equal to 0. So the nematic is aligned along the parallel. And you get more configurations. So, okay, for c equal to 0, again, the catenoid. Sorry, I'm not very good at drawing, but this is a catenoid. For c greater than 0, but less than 1, you get exactly the fatter catenoid. Okay? So this is for c equal to 1. For c equal to 1, you get the cylinder. Now, for c bigger than 1, what you get is a concave solution, which looks like that. And for c reaching plus infinity, the solution is a sphere satisfying the boundary condition, because you have to require that this graph must satisfy the boundary condition on the two coaxial rings. Okay? So this is what they did, just deriving the Euler-Lagrange equations and studying the solution of the Euler-Lagrange equation numerically. Okay? So our aim. Okay. Ooh. Okay, our goal okay, is it possible to provide a rigorous derivation? So what they did is just solving numerically. Is it possible to prove existence of minimizers and showing some of this behavior from a rigorous point of view, from an analytical point of view? So I just wrote rigorous. Okay. Is it possible? Yes, but with or at least in this first paper, with a first simplification. So first simplification, which actually I have to be, okay, I don't like it, this approximation, but we need to make, because we need to make it to start this study, which is the fact that we consider the covariant derivative. Obviously, for those of you, I know that this hypothesis, so as differential operator, we consider the covariant derivative is not the best approximation that one can do, but is a starting point. Okay, so this is the first hypothesis, and so our energy functional in this setting simplifies because it is given by the area term plus prime square plus alpha prime square divided by Okay? This is the, okay, here I'm writing the energy functional, erasing the last line because we consider the covariant derivative of the differential operator. And we make another hypothesis, which actually is the fact that if you don't assume any boundary condition on the angle alpha, since all quantities here are positive, you can decrease the energy by taking just the first and the second term. So it is rho divided by 1 plus rho prime square plus c rho prime square divided by rho square root of 1 plus. So this fact has been done just by the fact that we do not put no boundary condition on the angle alpha. And so if you don't put any boundary conditions, obviously it's more convenient to cancel these terms and just consider the two facts. So in some sense, we obtain an energy functional which depends on a constant c, but it is a geometric energy functional because the only independent variable that appear here is just rho, so the graph function that describes the surface in the revolution setting. But what you can see is that there are still the presence of the nematic contribution coming from the fact that the constant c is present. Okay? Good. So I hope that I said everything on the setting of the problem. Yes, okay, and this is what I want to stress is that is a geometric energy functional. Okay? Good. Yes. Okay. So what we did, so what is our aim? Okay. So what is our aim? We want to minimize this functional, so it is the integral of the area in this space where rho is a W11 function. Rho is strictly positive because obviously here you have a denominator, so rho cannot be equal to 0 because otherwise this energy functional is meaningless. And you have to impose boundary condition. Okay? So, and what you can see from this fact is that this is not BV. So we are not minimizing in BV, but in W11. So this makes difficult in getting compactness. And this constraint is not closed. Okay? So these are the two main difficulties that we need to take care. Which is our theorem? Okay, our theorem says if the ratio between H and R is small enough, now I'm right in this form. I will be clear in a moment. So if we are in this regime, so small enough means that the two coaxial rings are close enough. Okay, then there exists a minimizer, which is the set? Yes, okay, no, made a mistake. Then for all C greater or equal than 0, so for all values, there exists a minimizer okay, of this energy functional with this property. The minimizer is even, strictly convex, C2, yes, for all x in minus HH, so for all x, what we have is this inequality. So of x is less than R. I will be clear in a moment this inequality. I will explain it with a picture. And the last one is that rho C converges uniform to R as C goes to infinity. Okay, sorry. I'll write in a different way because I want to rho C tends to R as C goes to plus infinity. Okay, so you have 1, 2, 3, 4, and 5 properties. Okay, so our theorem says that there exists a minimizer with some geometrical properties. This inequality is fundamental. So what is rho 0? Rho 0 is the stable catenoid, so the unique minimizer in this setting. So what I'm saying, yeah, it's hard to make a talk with this blackboard. Okay, what I'm saying is that if what this inequality is saying is that if R is the ratio between R, H and R is small, so we are in the regime that is equivalent to say that there exists a unique minimizer for E0, which is the stable catenoid. So we are exactly in this regime, and I'm defining this minimizer as rho 0. So this inequality says that our solution lies strictly above that the catenoid, and they touch just in the 2 boundary point. So a graphical representation of our result is of this form. So minus H, H, R. So this is the catenoid, the stable catenoid. Stable. Okay. Our solutions, all solution for C strictly greater than 0 lies above the stable catenary. Okay? As C goes to infinity, they approaches to R, and as C goes to infinity, we get exactly the cylinder. There is one thing that we are not able to prove, but okay, there is one thing that we are not able to prove. Numerics says that this holds from a rigorous part we are not able to get, which is this one. So this is rho 0. And let me draw to, I need another color. 2 solutions. So let me call this rho C1, so C2, sorry, and this is rho C1. Okay. One would like to expect a sort of monotonicity with respect to C that says that if C1 is greater than C2, then rho C1 is small than rho C2, but unfortunately we are not able to prove that. And the reason for that is that we do not have an explicit formula for C. So differently from the case of C equal to 0, when you have the Euler-Lagrange equation and you can integrate the Euler-Lagrange equation, here we are not able to integrate the Euler-Lagrange equation, and so we do not have an explicit formula for minimizer. And so since we don't have this property, we cannot compare different two solutions with respect to the parameter C. Okay? So, okay, I would like to give you just one idea. So I just explained what so the ratio between H and R is small means. I want to give you one idea, which is fundamentally improving this theorem, and then I will advertise my last paper, my next paper that I hope it will be on archive in the next weeks. Let's hope. But okay, so I'm saying that there are too many difficulties in minimizing this energy functional. The first one is that we are considering functional in W11, and the second one is that the constraint is not closed. So how is it possible to get compactness, which is the hard stuff? The idea, which I think is a clever idea, is to use the stable catenary as a barrier from below. So I just draw picture. I don't write any proof, I just draw pictures. So our proof passing through this idea, so if this is my stable catenary rho 0, and I consider a solution rho C of this form, okay? I wanted to exclude the fact that the mice minimizer can go below the stable catenary. And now, if you define rho tilde, okay, let me call this minus H, minus A, and H, like rho 0, rho C, and rho 0, yes. So I'm taking this function. So I'm taking the catenary, then the solution rho C, and then again the catenary in these intervals. What we are able to prove is that the energy functional computed in this new competitor is less than or equal than the energy functional on rho C. Okay? And this can be done by hands, assuming, and this is fundamental, then this is small enough. Okay, I don't want to write, but in the ratio when the rho 0 is the unique stable minimizer for the area problem. Okay? And this, okay, maybe here I'm little cheating a bit because I'm just drawing examples which are convex, but believe me that the energy decreases by convexification. Okay, this is just a technical part, if you don't care, okay. Okay, the last thing, because I promised at the beginning of my talk that I proved that Jomi was wrong, is that, no, because I wanted to be, stress this. Why? Because if you derive, so this is our theorem, so you minimize this and you derive Euler-Lagrange equation. So if you derive the first integral, what you get is that the first integral satisfies this equation, rho prime square divided by rho 1 plus rho prime square to the 3 half minus rho, okay, no, okay. Minus rho divided by square root of 1 plus rho prime square is equal to a constant. Okay, don't care about what is this constant. But okay, any minimizers of this energy functional are solutions of the first integral. Okay, this is classical. But what you can see is that every time, so this is the nematic constant. So every time C is greater, is positive, and you try to put a solution, a Catenode solution of the form a constant hyperbolic cosinus of x divided by a constant, and you try to put this, what you get is that this solution is no longer be a solution of the first integral. So this means that even if C is small, a minimal surface cannot be a solution of the first integral if C is positive. Okay? Good. Okay. Should I have 10 minutes? Yes, okay. Yes. Okay, in the last 10 minutes, I want to, okay, this is the result that appeared on arXiv last year, but together with Chiara, Alfredo, and Luca, we are still working on studying this energy functional, and what we are able to do is to consider, so this, if you remember, has been derived for the surface gradient. So for the right differential operator that one has to consider on the surface. So what we did, and this is a theorem, again with the same people, let's be optimistic, is this one. Okay, I'm losing. Okay, no, this is. The idea is, okay, we consider a specific case of the alignment of the angle with the parallel, which is alpha equal to 0. So if you put alpha equal to 0 in this energy functional, what you end up is, let me call again E of C of rho. Okay, maybe it's a different energy functional, but I don't change the name, is of this form. It is rho plus C divided by rho, square root of 1 plus rho prime square. So in the specific setting of alpha equal to 0, so N is aligned along parallels. What you get is that you get exactly this energy function. And why, okay, one can ask me, okay, why you are considering a specific case? Because I think the result is more interesting because we are able to say more with respect to the covariant derivative. Why? Because the theorem is the following. So again, we minimize this in the same set, which I erase, obviously, in W11. Rho is strictly positive, and you must satisfy the boundary condition. Okay? What we are able to prove is that for all C greater than 0, okay, remove C equal to 0 because I've been already studying in the other paper, there exists a unique minimizer for EC, okay? And not only we are able to derive the explicit form of rho C. Okay, if you want, I can write it. It's something complicated, but okay, it's this one square root of cosinus, hyperbolic cosinus of 2x divided by E plus E square minus C, where this constant E is the constant that comes from the first integral. Okay, this is a constant coming from first integral. Okay, so in some sense, okay, in this case, so for a similar energy functional, okay, we are making an hypothesis, which is the fact that we are asking that that N is aligned along parallels, so a specific value for the angle. We are able to prove that not only there exists a minimizer, but there exists a unique minimizer, and such a minimizer has a specific form. I just wanted to draw the picture of the solutions, and I write here because you can compare the result on the covariant derivative with respect to the one that happens. So our solutions are exactly of this form. So minus HH, you have always, oops, maybe minus H. Okay, this is always my stable catenary. Okay, and our solution are, for a small c, we get the fatter catenary. For c equal to 1, the cylinder, so this is 0, less or equal than c, less or equal than 1. This is for c equal to 1. And then, increasing c, we get a concave solution. And we are able to prove that as c goes to infinity, thanks to a gamma convergence result, the solution looks as a sphere, satisfying, obviously, the boundary condition. And so this is the complete picture that we are able to prove for the covariant derivative and for a specific value of the surface gradient. One curiosity about the proof of that theorem, of this second theorem, is that is quite different with respect to the one that we did in the previous result, because you can rewrite this term as a length on a Riemannian manifold, and since the length is the invariant over manifold, this helps a lot in getting compactness for this energy function. So in some sense, this is a sort of, this term is a metric G, a suitable metric G with some hypothesis on a Riemannian manifold, and you can interpret this energy functional as a length on a Riemannian manifold, and this helps in the minimization. Okay, this is one thing. The second part, the secondary part is proving this, so that the minimizer is unique. And why is it so difficult? Because, okay, imagine that we are able to prove the existence of minimizer, and okay, it's not completely difficult, but it can be done. And then you derive Euler-Lagrange equation. What you end up is that Euler-Lagrange equation, fixing different values of h divided by r, so fixing different values at which the two coaxial rings are close. There are many, you can have 2 or 3 critical points, and proving the existence of minimizer, you have to be careful and you have to perform a fine analysis on the energy on each critical points that you end up solving the Euler-Lagrange equation. And finally, yes, I finish, I promise. And finally, this is a sort of, okay, we are just considering a specific case of the surface. What one wants to do is want to generalize the type of surface, not just consider a revolution surface. The idea is to interpret the first functional that I write. Yes, employing a sort of approach with harmonic map to studying exactly this energy function. And this is something that we are working on, to generalize this problem with a more general surfaces in which maybe you don't have to assume the fact that the surface is a revolution surface. And with this, I stop and I thank you for your attention.
Thanks, Giulia, for your nice talk. Are there questions, comments?
Thanks, Giulia. So regarding the last comment, so the first step would be to consider like the parametric approach.
Exactly. The idea is to parameterize the, so to employ for the area is exactly the Douglas-Rado approach. And the problem is to rewrite this in the parametric approach, so using the right metric on the disk in order to write this. Something has been done, so we did something, but Yes, but I don't, okay, I'm not feel completely confident in saying more than this, okay, but we are working on that. So yes, and the first approach is exactly using what Douglas and Rado did for just for the area to coupled with the part of the nematic vector, yes.
Thank you.
So comparing your results to the numerical evidence that you showed us during the talk. So it seems that your second result for alpha equal to 0 aligns with what they have seen in the numerics. So about the other one, I mean, it seems to me that in their case, I think it was alpha equal to pi half. This seems sort of to correspond to what you did in the covariant case. Do you have an idea why?
Okay. First, I would like to say that we tried to consider the right surface so the surface operator also with pi equal to 2, pi over 2. Sorry. What happens is that here this term is becoming quite hard because it multiplied by rho, so you lose coercitive. Okay, also there you lose coercitive, but you can recover there. Here we weren't able to apply the same trick that we used to make the barrier, and so what we realized is that okay, we forget about this and we studied just the covariant derivative and we saw exactly the same behavior. What I personally think, I think that this term, when alpha is equal to pi over 2, counts less with respect to the other. This is my impression. So in some senses that this is the term that counts more also in numerics with respect to this when you, because I don't know why, but maybe this counts less counts more with respect to this in the covariant derivative. This is my impression, but yeah, this is the reason. We started with this one, studying exactly the result with pi equal to 0 and pi and alpha equal to pi over 2 and alpha equal to 0. The other one we did. With this one, there are problems in applying our trick for using alpha naught as a barrier from below for this time of term, because it goes in the opposite direction. Because here you have rho at the denominator, here you have rho at the numerator, and so since it works so that here is becoming okay. So, but my impression is that this term is dominating.
Thanks. Further questions? Okay, if not, then let's thank Giulia again. All right, so the final talk of the day will be given by Antonio Tribuzio from the University of Bonn. And he will tell us about rigidity and flexibility in martensitic materials.
Okay, thank you very much for the introduction, Manuel. And thanks also to the organizers for the invitation and also for this wonderful workshop. So it's been super nice 4 days, and also tomorrow will be very, very nice for sure. Yeah, so today I will talk about some results in collaboration with my postdoc advisor, Ankana Roland, about energy scaling laws in elasticity for very highly non-convex elastic energies that arise in the study of Shea memory alloys. And yeah, maybe if there will be time, I will also talk about at the end, I mean, just giving hints of some new results that we obtained recently. As a continuation of this a bit older result. Okay, so maybe in the first slide I will just give you a bit of the context, that is to describe this type of materials, these Shea memory alloys, that are materials that whose crystalline structures behave in a very particular way, so it's kind of affected by their internal temperature. Indeed, at a relatively high temperature, these materials have a very highly symmetric crystalline structure. For the moment, we can really think at the cubic lattice, and this is the so-called austenite phase. But when they are cooled down, their crystalline structure may lose some symmetry, and due to this lack of symmetry, they may present different but energetically equivalent crystalline structures. And this low temperature regime is called the martensite phase, and sometimes these different structures are referred to as martensite variants. And okay, so the feature of this material is that if this crystalline, so if these variants are sufficiently compatible, they can concatenate at very small length scales leading to the formation of microstructures. And somehow these microstructures are responsible for very interesting macroscopic effects. For instance, the very well-known effect is the shape memory effects, which also give names to these materials. That somehow consists on the fact that at the austenite phase, you can kind of impose to your sample of your alloy a shape, then you cool it down. In this way, it's a bit easier to deform it, and then when you heat it back up, it recovers its initial shape. Okay, and somehow, since these microstructures is kind of understood that are responsible for this stunning behavior, that of course is very important in applications, then from a mathematical point of view, we are interested in studying some properties of microstructures. Okay, so this is what this talk is about. And okay, the usual somehow references for introduction, both from a modeling point of view and a mathematical point of view, to this type of materials are the wonderful notes from Müller or the book from Bhattacharya. Okay, so we said, so this is a workshop of calculus of variation. So of course we want to study these materials from a variational point of view. So we follow the approach of Ball and James. And the context is that of continuum elasticity. So we consider somehow our deformed material to be described by the deformation map, and to each material we associate an elastic or internal energy, which is just the integral over the reference domain of an energy density, which depends only on the deformation gradient. In principle, of course, for this property that I showed you before, the energy density depends also on the temperature, but here we are assuming that somehow the temperature is fixed and low, and we are in this regime in which we have all these different preferred structures. And okay, so this energy density, to be kind of realistic, should satisfy some symmetric assumptions. Also, yes, this was this usual framing difference already Emmanuel kind of described a little bit. So this is invariance under left multiplication of the rotation, in the sense that if you take your material, you deform it, and then you rotate it. Of course, this rotation should not affect, so should not change the elastic energy. And then there is also this right invariance this invariance under right multiplication of some rotations, that are those that somehow fixes the kind of, so this depends on the material, so this kind of point group. So it's the same one that introduced also Sergio this morning, but now we are interested in keeping the volume, so in conserving the volume. So this is a subset of the rotation, and these are just the rotation that fix kind of this the lattice of the material. And then, so this just means, so this can be considered as a fact that each of the Martenside variants have the same elastic energy contribution. Okay, so for this symmetric assumptions, the prototypical energy density is really, so can be really considered as the distance of the deformation gradient from a set of matrices, that is the set K, that is the so-called set of stress-free states. This is just union of somehow copies of SON that comes from this framing difference, and these AI are just the affine matrices which characterize the lattice of the Martenside variant. Okay, so of course the modeling hypothesis is that the material would like to accommodate minimizers of the elastic energy, and it's already a couple of times that I dropped this word, the microstructure. So in this mathematical context, I have to explain what is a microstructure. And okay, somehow the complexity of the answer depends a little bit to whom you're asking. Because for instance, if you ask to Roberta Marziani, one of the organizers, then the answer is pretty simple. A microstructure is just something very, very small, but okay. So this is, okay. So this joke I can do only when Roberta is in the audience, but especially if she's organizer. But okay, so this is not the definition that I'm gonna use for this talk. I would rather say that microstructures are minimizers or minimizing sequences of the elastic energy, which present very fine oscillations. And okay, by this so we said we want to study microstructures. So I have, okay, so this is maybe kind of a justification of the fact that these models naturally present microstructures. This is a bit kind of for an audience of this conference. Okay, maybe it's kind of easy, but it's good to fix ideas a little bit. So here, the thing is that we want to minimize, we want to consider minimal elastic energy configurations, but of course, so this means that we are minimizing an energy whose energy density is not convex, right? So it's not even quasi-convex, so it's highly non-convex. So of course, the minimization brings oscillation. So this we can see really with this super easy toy model. So we are in the unit square, even scalar valued deformation. We take, for instance, the elastic energy, which is somehow a penalization from the gradient 1, 0 and the gradient minus 1, 0, and we put zero boundary condition. Of course, to take, so here we can prove that elastic energy, so the elastic energy does not have a minimum, because to minimize the elastic energy, you want to somehow laminate between these two gradients, and this is not compatible with the boundary condition 0. And then this is the reason for which somehow we have to put some cutoff here, close to this horizontal boundary of the domain. But of course, so the elastic energy is non-zero of any, for instance, H10 function. But of course, by increasing the frequency of the oscillation, this cutoff term becomes smaller and smaller. So the elastic energy becomes smaller and smaller as well. And so we are going towards the infimum, which is 0. And of course, I mean, this is not somehow in the limit, we just get 0. Okay, this is not lower semi-continuous, so 0 is not a minimizer. But somehow, since we started from a very realistic model, this is not very realistic, because somehow we are saying that if we just consider elastic energy, then a microstructure should have finer and finer oscillation to be the optimal one, but this, of course, is not what you see in materials. So in materials, you see really some lamination at some finite length scale, so that you want to be your kind of optimal microstructure. So this is already a first problem that arises in this type of energies. And okay, so this is just a remark that this is just, okay, you don't see it because this is really a scalar problem, but we are going to consider vectorial cases, and then in the vectorial case, even lamination is not always possible. Your somehow wells should be rank 1 connected, okay, by the Adaman jump condition. Okay, so this is already a first somehow problem that we immediately identify by elastic energy, but also this justifies the fact that microstructures, so some oscillation should appear. Okay, but now we want to study this type of microstructures, and already we see that somehow, even if we consider a very specific type of solutions that are so-called exact solutions, so the solutions that comply with elastic energy to be exactly equal to 0. So here we are forgetting boundary condition. So we are like considering microstructures that are locally minimal. And these are solutions to, so for instance, we consider an easy, I mean, quotation mark case. So when the set K of stress-free states is just a double well, okay, here even to 2 by 2. Then the solution of elastic energy equals 0 are the solution to the differential inclusion almost everywhere of this type, okay? And okay, this determinant condition is just, forget about it. It's just to ensure that you have rank 1 connections between the wells, but you can also remove it somehow. And then, okay, so these are somehow, in our definition, are some microstructures. But here already we see that this type of problems present a dichotomy according to the prescribed regularity of this solution of this differential inclusion, okay? So for instance, the result from Dotsman and Müller says that if you prescribe a BV regularity of the gradient, and this is somehow very realistic because you want to say that, so the number of the change of phase in your material, so the how many times your material laminates is kind of finite, or you can control it. So this is a really realistic hypothesis. So if you impose, so if you check for solutions of this differential inclusion with gradient U to be BV, then there is only one class of solutions that are locally simple laminates, okay? And this thing, so the existence of only one class of solutions, we refer to in this talk at least to as rigidity. So if we impose our microstructure to be with gradient BV, there only one class of solution exists that are the simple laminates, okay? But also, this somehow was surprising. Even in the title of their paper, Müller's Verak, they wrote something like unexpected solutions or something like that. If you completely drop the BV regularity of the gradient and you just consider Lipschitz solutions, then a large class of solutions may appear. That's okay, they are obtained via very complicated algorithm that is this convex integration that somehow says that you have to develop a lot of oscillations in also very different directions, and this you can prove that are nowhere laminates. So okay, so there are so this means that you have simple laminates as solutions, but also a big other class of solutions. So so this is what we refer to as flexibility. So you have different classes of solutions. Okay. So somehow already mathematically you can ask yourself, okay, then what? So is there a threshold regularity? So between these two regimes. So because here for gradient L infinity we are in the flexible case. For gradient BV we are in the rigid case. Kind of mathematically you can ask, okay, is there maybe a threshold regularity of the gradient for which you can claim that below this threshold regularity you're flexible, above you're rigid. So this kind of mathematically makes sense, but this has also yeah, nowhere laminates. So it's I think in every point you find a ball. So for in any point and in any ball you're not a laminate. So you're not a function depending only on one variable. You can sorry. You are like, or you can have a laminate of higher order. Okay, this is not for every, so here I've been a bit sloppy, this is not for every boundary conditions, but if you take boundary conditions sufficiently somehow complicated, then you can find solutions that are nowhere laminate somehow. Okay. Okay, but this is just to say that yes, there are two classes of solutions somehow, and then you want to understand whether you can find so yeah, a threshold regularity. Okay, so this is somehow a mathematical question. Okay, as it is posed, is not super well posed, but I have been a bit also sketchy on this. But this somehow has also a counterpart in applications, if you want. That is somehow whether so which of these microstructures, so which of these minimizers or minimizing sequences corresponds to really realistic microstructures that you really see in materials, so that are physically relevant. For instance, this you can regard as a rigid case, so somehow, okay, you do a refinement towards the boundary because the thing is a bit more complicated than I presented, but here you see that you have kind of a laminate, okay? This is an experimental, very famous experimental picture by Kuhn James, or whether something like this, this is just a numerical, is a numerical picture from Inamura's group. So if you can have something like this, something in this direction, that this should be the flexible case, okay? So whether this type of microstructure you can really see in some materials. Okay, but for all what we said, elastic energy alone cannot give you, I mean, such an information, because somehow we saw already that the elastic energy lacks of a length scale, no? of a natural length scale of in its model, because somehow if you send the oscillation to 0, then you are getting better and better, so lower and lower elastic energy. So the way that you usually study this thing is to regularize your elastic energy. So you add a higher order term, so a term in for instance, in the action of the deformation, which penalizes change of phases, okay? And of course you multiply, so this is the so-called singular perturbation. So you take epsilon, which now stands for a length scale, so you're kind of enforcing a length scale in your model, and then this is of course supposed to go to 0 somehow, or to be very small, and then you add to the elastic energy a higher order term, for instance, the total variation of the action multiplied by epsilon, okay? And this somehow is, I would say, the standard way since the pioneering work of Kohn and Müller. Okay, so this is somehow a model which is a good approximation of what is supposed to be what is happening in materials. So what now we are going to do with this singular perturbation energy? So the first step in understanding the asymptotic behavior of these energies is to study scaling laws, okay? So this means that you do the inf or the mean or whatever of your deformations under some boundary conditions, and you want to study to see with which order of epsilon is this somehow number going to when epsilon is going to 0, okay? And of course, so, and actually recently this I mean, well-studied question. Here I put some kind of papers that or kind of focus on some groups that I know that are working on it. Of course, the work of Kohn and Mueller, the one who initiated this kind of analysis. Also the work of Laurent, who considered also relation with discrete models. The work of Otto and collaborators, Hans Nuffer, also together with Kohn, also with Otto. Of course, the work of Sergio, and then also of Barbara and Janusz in Berlin. Okay. Oh, now I think, of course, also Teresa. I mean, say that you are in the group of Otto. Let's say that. It is also a super interesting result that I'm actually even reading at the moment, and then okay, I forgot to cite. I'm sorry. Okay, so a lot of very strong people are studying it at the moment. Okay, so this is kind of okay. So this is what you usually do. You study scaling behavior. So what is the relation between scaling behavior and this mathematical question that I kind of storytelled? I mean, in the first slide. So this threshold regularity. Okay, this comes from a very nice result from Ankana Ruland, Jamie Taylor, and Christian Zilliger, kind of recent somehow, in which they relate scaling laws with this threshold regularity of the underlying solutions to the differential inclusions. Okay, so if you have, you consider, E epsilon is a bit different, but it's some kind of a singularly perturbed energy with stress-free states K. So if you have solutions to the differential inclusion that are whose gradient is HS regular, then you can kind of mollify this solution, you plug it into your energy, and this is giving you an epsilon 2s upper bound. So if you have solution with some regularity, you get an upper bound. And they also note, make the remark in the paper that you can use it kind of on the other way around. Okay, so in order to, let's see how. So if you use it kind of in the, how you say, in the converse way, so this is giving some information on the threshold regularity of your solutions, because you say if you had a lower bound and then you have solution to the differential inclusion, okay, then the regularity of the gradient cannot be more regular than HS. Okay, here HS is in the sense of fractional Sobolev regularity. Okay, so somehow this is saying that if you have a lower bound, then you have somehow an upper bound on the threshold, so on the regularity of your differential inclusion. So somehow this is one way, so to get information on the regularity of this threshold regularity between rigidity and flexibility. Okay, you can also study scaling behavior of the associated singularly perturbed energy. Of course, there are also some, you can get also some other more concrete informations in terms of the model, so the physical model, that is study of length scales of microstructures. So, okay, so it's interesting to study energy scaling behavior of these energies. Okay, so I hope I convinced that this kind of question makes sense. So as we saw, so we want to understand a bit whether, according to the model that we take, we are in the flexible case or in the rigid case. And we saw, okay, kind of convinced you that in the flexible case, so with this kind of convex integration solutions, then you kind of somehow develop a lot of oscillations, very complicated, one on top of the other, or of high order. So this is kind of the type of model, so the type of microstructures we want to study. So we are looking for, so we were looking at the time, and okay, now we got the result for a model who naturally gets this high order of lamination when you're going to minimize the elastic energy somehow. And so the model was already there, was kind of a 2x2 diagonal, so model 2x2 set of 4 matrices, even diagonal matrices. It was proposed by Tartar, was something similar. I don't know if with exact the same numbers, but was proposed also in a PhD thesis of Schaeffer, so I put it there as a reference. And okay, so it's this set of 4 matrices here. Okay, here now we remove the SO2 invariance to make things a little bit easier. So it's the set of 4 matrices here, A1, A2, A3, A4. They're here. So we can draw the picture. And the main feature of this set is that they are not rank 1 connected, okay? Because here diagonal matrices are rank 1 connected only in vertical and horizontal direction in this picture, so in this the plane of diagonal matrices. Nevertheless, the rank 1 convex hull is non-trivial and is exactly what the picture that I put here, okay? So, okay, so this is one way to say that if you want to go to minimizing sequences, then you have to develop, you cannot really do easy lamination because these matrices are not rank 1 connected. So you have to create something a bit more complicated. Okay, another way a fancy way to relate this Tartar square to our question of rigidity and flexibility is the following one. So this comes in the somehow maybe in the context of TN structures that I really don't want to introduce, but okay. So somehow you can say that this set of matrices is at the same time rigid and flexible if you change a little bit the meaning of rigidity and flexibility that I told you so far. So is rigid in the sense of the exact solutions, in the sense that the solutions to the differential inclusion are only affine matrices. So you have only one class of solutions, affine matrices, so gradient constant. But is somehow flexible. You have a lot of minimizing sequences in the sense of approximate solutions. So sequences whose elastic energy is going to 0. Okay. In this case, you can, and we will see an example later, you can find solution whose gradient do not strongly converge to any function, so are not really a perturbation of the affine of an affine matrix. Okay, and this is somehow the counterpart of saying that the lamination convex hull is trivial because I mean the function, so the matrices are not rank 1 connected, but the rank 1 convex hull is non-trivial. Okay, so this is the set we decided to focus our study in order to give an attempt to improve the knowledge between this dichotomy. Yeah. Very good question, Pascal. No, it's okay. So this is the this is the lamination. I'm joking. No. This is the lamination convex hull. So somehow you can obtain. So it's somehow a convex hull. Okay, not convex in the sense of convex, but in the sense of rank 1 polyconvex. It's a hull. So that you can obtain it by an iterative definition. So somehow contains all the laminates all the affine matrices that can be kind of the weak limit of laminates, okay, that you can build with the set of K. So what does this mean? That usually you take the set K and then you consider the first order lamination convex hull as the Fs who can be written as convex combination of element of K that are rank 1 connected. Okay, so and then you do iteratively. So then the second order is those of the so you do the same thing but with the element of the first order lamination convex hull, and then you go up to infinity. Of course, to start this iterative process, you need to have at least one rank 1 connection. Otherwise, everything is empty. So this is somehow the thing that okay, at least in this easy, maybe another more complicated situation that I don't have in mind at the moment, maybe it's not completely true, but at least for this example it's true. So here you don't even start this iterative procedure. So K is KLC, the lamination convex hull equals K. Okay, but thanks for the question. Okay, so this is the set. So let's now be a bit more precise. So let's set our problem. For simplicity, we are in the unit square. We consider periodic deformations, and we put an average constraint on the gradient. And this F is a non-trivial element of the rank 1 convex hull. This will kind of never enter in the game anymore later. So we can really think that F is 0. Okay, so it's 0, it belongs to the rank 1 convex hull. Okay. Okay, and so this is the energy that I said we want to start. We want to study is not exactly that. So I will kind of slowly transition to the energy we are starting. So we said that we want to minimize our singularly perturbed energy in U, and then we want to study the scaling law. Okay, but now somehow here I will do a decoupling between the gradient, so the deformation gradient, and its projection of K. This will really help in our, so it's really helping in the study of this, especially of the lower bound. So I can rewrite the distance of the gradient from K as the distance of the gradient from any element of K. Then I switch this chi to functions taking values in K. And then this is all formal, but maybe, I mean, probably you can make sense of it even more rigorously. And then I switch the inf. Okay, so now I'm taking the inf over functions taking values in K of some functionals that does not depend on U somehow because we infimized. Okay, so now we pass from a functional in U to a functional in chi. And this chi represents the phase indicator. So it's just a BV, is actually SBV, so it's a BV function, is a BV simple function. So because K is the Tartar square, periodic, okay. And then this is the energy that we're going to consider that is kind of exactly the same, but here instead of the penalization given by the total variation of the Hessian of U, we take the total variation of the gradient of chi. Okay, but you can actually prove that, and this actually, this work with a PhD student of Ancana and also with Christian Zillinger. So the PhD student is Camillo Tissot, that we kind of explore a little bit when this scales the same and this, so all the reasonable thing that you can put here that converges to kind of the length of the interface somehow scales the same. Okay, and here just a remind, but also to set a bit the notation, I remind you that chi is taking values in the Tartar square, so it's the diagonal, okay? Chi1 and Chi2 will be, Chi1 or Chi2, okay, will be their diagonal entries. Okay, so this is our energy now. And this is finally our result, so with Ancana. Okay, this F came back, but who cares? So this is for every gradient, average gradient constraint in the rank 1 convex hull that is non-trivial. Somehow we have this, we have proved a scaling law, so upper and lower scaling bounds of this nature. So is this exponential up to a constant here of minus, so a log epsilon at power 1 half. Okay. Okay, here maybe I make you, so I noticed that actually this is not super clean matching upper and lower bound because here we don't have the power 1 half cleanly, but okay, in spirit we kind of consider it like matching. It's not, but okay. Now dropping you this scaling law without explanation makes no sense. So first, let's say we do a sanity check. So here epsilon is going to 0. Log of epsilon is minus infinity. We take we take the modulus plus infinity with the minus infinity. X plus minus infinity is going to 0. Sanity check completed. So this makes sense. But then also another important thing that we can say is that this scaling somehow it's going to 0 much slower than any power of epsilon. So of any power epsilon, so concave power of epsilon than any epsilon at power alpha. Why do I say this? Because I mean, who knows? I mean, this result from Kohn-Müller and also some result from Sergio. You know that somehow models which develop finite order of oscillations that have been proved so far, they were having somehow algebraic scaling. Okay, so this is really hinting on the fact that you're probably, so to go to the ground state, you need infinite order of oscillations. Okay, not only finite. And what is written here. And okay, everything is presented for the periodic boundary condition, but everything works also in this case for affine boundary conditions because the lamination is so complicated. Okay, so now, from now on, I will try to give sketches of the proof of upper and lower bounds. Yeah. So okay, one side, for instance, if you put zero boundary condition, then you can periodize it. Okay. So if you have, I would say, if you have the lower bound for periodic, then you have the lower bound also for the affine, and then the upper bound is actually proved for the affine, so you gain it also for the periodic. I mean, for models which develop lower order of lamination, this is not true. But for this, for some reason that it's long to explain, this is true in the Tartar square because the microstructure is too complicated. So periodic or affine doesn't change anything. Okay, thanks for the question. Okay, so the upper bound somehow was already well known in the literature. We didn't know it. Luckily, we got the same scaling, so everything went for the best, and was provided by Winter and from Shippo even in the discrete setting, and this kind of goes like that. So here is what is happening in the codomain. Here's the definition of the function, and then I try to also show what is happening in the domain. Then I will get also at the blackboard. Then we get also a picture later. So somehow we said that 0 is our average or boundary condition. We want to approximate that, but with low energy, no? So we want somehow to, and this is kind of also the idea of convex integration. So we want to approximate 0 with something that is closer to the energy. So an example is this one. Okay, so I do a lamination. So this is my domain. And then I do a lamination between these two B0 and B1. Their energy is still non-zero, but they're a bit closer to the wells K. Okay. But then I realized that I can proceed this further because B0 and B1 I can again approximate with something that are closer to, thanks to lamination, that are closer to the set K. And so what I do is that I replace, maybe here I'm B0, here I'm B1, I replace B0 and B1 with a second order lamination going in the opposite, so in the opposite direction. Okay, but now, why do I gain now? Because one of the two elements I'm laminated with is a stress-free matrix. So the energy, so when the gradient exactly equal to A1 or A3, I'm paying 0 elastic energy. So for the rest, I'm paying. So let's say that maybe here, on this, somehow on this kind of stripes, the gradient is either A1 or A3. So the gradient belongs to K. So I'm paying 0 elastic energy. So whatever, so the elastic energy term somehow now goes like 1/2 of the domain. So the 1/2 the measure of the domain. Okay. So in 1/2 the measure of the domain, I'm outside the Tartar square. So I'm paying energy. When I'm inside the Tartar square, the elastic energy is 0. Okay. So I reduced kind of the energy. Okay. And then I can proceed once again by doing lamination. So by replacing kind of the lamination in which my deformation is not inside the Tartar square. Okay. And by doing this, somehow the elastic energy, so let me write maybe like this. The elastic energy of U is kind of proportional to the area in which the U does not belong to K. And this now I even reduce by 1/2. Okay, it's measured. So now it's going to 1/4. So you see that I can continue this process. I can iterate this process. And by doing this in the limit, so the measure of the set in which my differential inclusion is not satisfied is going to 0. So somehow this is a minimizing sequence for the elastic energy only. So this was already, so at least I saw it the first time in Müller's note, so I guess it was already well known, but then was quantified by Winter. Okay, so this is just quantification of the singularly perturbed energy of this well-known construction. Depends. So in principle, if you have the singular perturbation, so in principle you can send to the limit somehow, as well like for the two wells you do the lamination. No, but then you continue. It's kind of, so even if you cover everything, So now, I don't know, now what is, it's blue. And now I approximate again where gradient of U equals P1. I use again these two matrices, and I continue in this way. But this now, so when I use first these two matrices, I was in one part of the domain. Then this part is kept fixed, and then this P2 is replaced by this lamination. Okay. So maybe what is yeah. But the measure is not fully covered. The measure of the domain. I don't know if you. So it's this picture here. So this picture here now, the measure somehow. So this part is covered. So inside here, up to cutoff, okay, the gradient belongs to K. Right? Inside here, the gradient belongs to K, but here no. So now it's inside here that I'm doing again a lamination. Okay, so this. But okay, so this is well-known somehow construction. Okay, so and in the limit, and then the limit somehow this measure goes to 0. Okay, so now it's kind of a quantification of this process that I do here. So let's say the nth order of lamination. So this is kind of this picture. So the volume, so the elastic energy term is this one. So I have a volume term that is essentially where the gradient is outside K, that goes like 2 a power minus m. And then I have this R that just comes from a cutoff procedure, because of course these laminates then they have to attach, because inside the domain I want to be Lipschitz, I want to be continuous. And then of course this term is just the surface energy, which goes like R at the power minus m. Okay, here what is R? R is the length scale of the first order of lamination, and all the other lamination is happening at order R at power m. So the second order lamination is happening at length scale R square, then the third order lamination is R cube, okay? So this lamination here is R, so order R. So the frequency is 1 over R for the lamination of the first order. Of the second order, that is this one, this is R square. Of the third order, that is this one, this is R cube, and so on, okay? So of course, the number of oscillations somehow is 1 over R, in this case 1 over R at power 3. If I did them, iteration is 1 over R at power m, okay, times epsilon. Okay, then you optimize this, somehow you then you optimize all the parameters here. You can first optimize the length scale, so the amplitude of the oscillations with epsilon. You obtain epsilon at power 1 over m plus 1, and then you optimize. So then these two kind of behaves the same, behaves epsilon at power 1 over m plus 1, and then you optimize m, so the order of lamination that you have to do. That then in this case are finite. Okay, they are just very, very, very large. Okay, because it depends on this factor here, epsilon. Okay, then by optimize everything, the number of oscillation that you have to, so the order of lamination that you have to do is this one. You plug this in, and then you get the upper bound. Okay, so this account some kind of the proof of the upper bound. Okay, this is done. So now lower bound. So let's start with some kind of rough ideas. So the first thing, and then this will be kind of, kind of super sketchy. Is that, so I will just give some something, so want to point out some property of the Tartar square that we will use in the lower bound, okay? So let's check how to get that the exact solutions are rigid. So okay, we consider solutions to the differential inclusion. Since K is diagonal, then the off-diagonal components of the gradient are 0. But this means that U1 is a function of x1 only, U2 is a function of x2 only, and then their diagonal entries are also functions of x1 only and of x2 only. And now gets into play the structure of the Tartar square. So the structure of the Tartar square, maybe I go back 1 second to the picture, also here, is that if I give you any entry of the element of the Tartar square, you can give me you can tell me which matrix I'm talking about. Okay, so there is a one-to-one relation between the first entry and the matrix, as well as the second entry and the matrix. So this means that somehow a function taking values in K, so it's one-to-one with functions. So what I want to say, so okay, let's keep this information so that that somehow if I give you the entry, then you tell me the number of AJ that I'm in. Okay, but now if the first entry depends only on x1, then the full matrix depends only on x1. Okay, because if you know the first entry, then you know the matrix. So the full matrix is a function, so the full gradient is a function of x1 only, but for the same reason here, the full matrix is a function of x2 only as well. So this means that the gradient is constant. Okay, and this is really somehow super naive, but it's a tool or it's an ingredient that we're gonna use heavily in the lower bound. So the fact that the two diagonal entries of the Tartar square, here I write characterize each other, but in the sense that there is a one-to-one correspondence between them. Okay, so this is somehow solutions to the exact solutions, and somehow in the same way in which you transfer Liouville theorem to geometric rigidity. So our strategy to find a lower bound is to translate this into a rigidity estimate. So here we prove that solutions to the differential inclusions are affine. We want to translate in it, okay, the L2 distance of the gradient. So we want to quantify somehow this property, no? So the L2 distance of the gradient from, we will see that it will be the volume constraint F, so but in general a constant matrix, is controlled from above by a rescaled version of the elastic energy. So if then we prove that this is positive, then okay, we get a lower bound. And this is given in U, but I told you so that now we are working in chi, which somehow behaves like a gradient. So this is actually the lower bound. So the estimate that we wanna, the rigidity estimate we wanna found, okay, that will imply the lower bound. So this is our what we're gonna get. Okay, how are we gonna get there? We are using heavily Fourier analysis. Okay. So by kind of this decoupling, it's somehow a bit easier. So we can, in kind of an easier way, translate our elastic energy in chi from real space to frequency space in a kind of a very compact, way. And this, okay, for different type of energies was done at the beginning from Bob Cohn, and then also Capella-Otto used it a lot, also Nuffer-Cohn and Dotto. Okay, so, and here, okay, in this periodic case, it should hold really the equal sign up to the zero term that here I removed because, I mean, it was not fitting in the line, but so here you have the norm, so the average of chi, okay, minus the constraint, okay, we said the constraint is zero. Okay, how do we prove such a lower bound? So we take this, so we just rewrite this minimum problem in U in Fourier space. So we take this energy, we use Plancharel. Plancharel is, so now after Plancharel, the energy reads like this. You minimize it with, so by kind of, if you want, by indirect method. So by the Euler-Lagrange equation, you can either do the Euler-Lagrange equation here and then you do Parseval or do the Euler-Lagrange equation here somehow. The Euler-Lagrange equation is just a linear system in U that you can solve. And by solving this linear system, you get that each component of U is, okay, up to this constant here, is kj divided by k square, the Fourier transform of the jth entry of chi. Okay, then you plug this here into the Fourier representation of your energy, and you get this nice formula here. That I'm gonna maybe make sense of it or comment about it later. Yes. There is still some time, or yes. Very, very small time. Okay, so maybe here I can really go a bit. So somehow the elastic energy say that the lower bound it's somehow easy to see in Fourier space. We can also control from below the surface energy, and this is somehow also something that was obtained by Nuffer-Cohn-Otto, Cohn and Wirth. In which you can somehow control the high frequency, so the the tails of the Fourier transform of chi by just the total variation. This is just say that if your chi is oscillating a very high frequency, then of course somehow the total variation is somehow is giving a control of it, okay? Because when k is very large, so it means that you are oscillating with very high frequency, and of course this you have to pay with the gradient. Okay, so this is the proof. Maybe I skip it because it's yeah, but it's okay. So it's just you control so the total variation control finite differences by L infinity. This can be done with somehow we can go to growth 2. You do Plancherel, and then you can have a lower bound. Okay, so now these are the two estimates that we have, and then we can kind of so thanks to these two estimates, we can kind of somehow have an intuition on where. So if we consider elastic energy and also total variation that somehow are small, we kind of have an intuition on where the Fourier transform of the entries of the phase indicator is concentrating in the Fourier space. Okay, somehow. So if you see here, so if you imagine. So somehow the Fourier transform of chi11 is telling me, so if it is concentrating in a frequency k, then it means that in real space I have a lot of oscillations in direction k and that frequency k. Okay, so frequency modulus of k. Okay, so this somehow is saying that if chi11 is concentrating away, where this Fourier multiplier is 0, then the elastic energy is very high. So if I'm concentrating away of this axis, then this elastic energy is high. So since we are gonna focus on minimizing sequences in which the elastic energy is small, this means that the first component of chi is concentrating somehow around this x1 axis, the second component around this x2 axis. And this is also, okay, now I'm going a bit quick, but you can also kind of make sense of it because of the rank 1 connections inside your, so of diagonal matrices, okay? Okay, but this can be done, so by this lower control of elastic energy and surface energy, you can do it quantitatively. So you can define somehow this red cone, which is the cone in which chi1 is concentrating, with a precise spreading angle and with a precise cutoff. So this red cone is very thin and very long, in which chi1 is concentrating, and analogously for the other component. And by this, somehow we have something that starting resemble the estimate that we wanna get. So somehow we have that the L2 norm, so the L2 mass of our components of chi outside these cones is controlled by somehow energy. Okay. Of course, if now C1 and C2 somehow are empty or contain only the origin, then we would be done, okay? Because if they're controlling only the origin, then this sum becomes just the L2 norm of chi1 up when you subtract the average, okay? So the idea is kind of to scratch a little bit so the Fourier mass inside these cones, okay? And to get here a control of the full L2 norm of chi1 and chi2, kind of not losing too much energy here. Okay, so this is where kind of this characterization of the diagonal component of the Tartar square comes into play. Yes, so here we are using really, so we are starting kind of to try to reduce the localization cone of chi1, okay? So we are really using the fact that chi1 can be written as a function of chi2, in particular a polynomial, because so we have only, so they are taking only finite, a discrete set of values, then we can do polynomial interpolation, okay? But now polynomials are very, so by simplicity, I can consider this polynomial to be just the square, okay? And polynomials behave very well with Fourier transform, because if I have that chi1 is chi2 square, then I have also a relation between the Fourier transform, so that the Fourier transform of chi1 is the Fourier transform of k2 square so K2 convolve with itself. And here is kind of how our method of scratching somehow a bit of mass in this Fourier cone starts. Because, okay, K1, for simplicity, say that is localized here, but then and K2 is localized here. Then the convolution of K2 with itself is localized somehow in the Minkowski sum of this cone with itself, which kind of lies in this thick, so in this stripe. Okay, but since the convolution of K2 with itself lives here, equals to K1, that means that K1 should be localized in the intersection of this red cone inside this stripe. Okay, so somehow, yes, so somehow this means that K1 is localized in a smaller cone. And this procedure we can do, so the smaller cone is this C1 tilde, we can do by paying just a multiplicative constant here. Okay, so without changing the scaling that we have here in front. Okay. I really wanted to be not so naive, and I also did some computations that I am forced to skip because no, we can go. Okay, okay. I was trying. No, okay. So let's do. So let's try to be a bit more precise here. So okay, to be a bit more precise, I first define some notation that is the following. So the notation of Fourier multiplier. So somehow here I'm defining a Fourier multiplier which is just a convolution operator, okay, in L2, defined like this. So I just restrict my Fourier transform, okay, in a set, for instance, the cone C1. I do the Fourier transform back, and then this, by the property of the Fourier transform, is actually an operator of a convolution operator on phi. Okay, so this means that, okay, MC1 of Chi11, for instance, is just the function whose Fourier transform is restricted in the cone. Okay, so by just, and then I define this smaller cone, as I said, as the first cone intersected by C2 plus C2, so this stripe here. Okay, so with this notation, what I wrote here before the L, so what I wrote here can be just rewritten in this way. Okay, so because this is concentrated outside the cone. Okay, okay, so this is the thing, so the estimate that we have, but now we want to control the Chi11 in a bit larger set, so outside the C1 tilde, which is so it's smaller, so the counterpart is larger. Okay, but this we can split in whatever is outside the big cone and whatever is inside the big cone but outside the small cone. Okay, but now we are using really this picture. So the fact that this, so this function here, so by the rules of the Fourier transform that turns multiplication into convolution and so on, this function here is supported outside. So so because this function here is supported inside this stripe, and this function is supported outside this stripe. So here I have the L2 norm outside the stripe. Since this function in Fourier space are their support are disjoint, whatever I add here, I'm increasing the L2 norm, and by adding exactly this term, I recover. So I'm just adding some mass. Okay, and now what I do here, I sum and subtract by Chi11. So I get back this term that is nicely controlled, and then I have the difference between somehow. So the restriction in Fourier space of Chi22 in the big cone minus Chi11. And here we are using again the fact that Chi11 can be written as Chi22 square, because now you see that I have exactly this term, but between the squares. Okay, so now this is wrong, but it's just to simplify a bit things. So now we are assuming that we have some kind of a Lipschitz control. Then I can control this term with the original term that was already controlled, and not to pay a multiplicative function, a multiplicative constant, I have my upper bound of the elastic, so the desired upper bound. Okay, so this is one kind of scratching of so one cone reduction, but since this the diagonal entries characterize each other, I can really do also the other way around. So I can write Chi22 as a polynomial of Chi11, and I can repeat this thing infinitely many times or arbitrarily high number of times. So kind of in the same way we were doing the upper bound. So we get, and every time we're just paying a multiplicative constant here, we go up until the cones kind of reduces to contain only the origin. So here we get really the lower bound almost the lower bound we were looking for. And this you do by doing this procedure 1 over alpha times. Here alpha was some parameter that's going to optimize now. We optimize alpha in terms of epsilon, and we get actually, so this is a computation, you get actually the same scaling, so the desired scaling for the lower bound. Of course, the problem is that we cannot really use this Lipschitz control that I said before, and in this inequality, so in this inequality here, okay, you have some losses. So you don't have the pure L2 nor, but you have to pay some losses in terms of this power, in terms of this multiplicative constant, and this reflects on the actual lower bound. And then, okay, the rest is really okay, here you control chi from its average, but the average of chi is very close to the average of the gradient by Jensen's inequality. So here you really have so the control of chi minus f, since f is not in k, so this is chi taking values in k, so this is bounded below. And we get the lower bound. Okay, so this is really, so maybe in a nutshell I can say that, so this is the end, somehow we proved upper or lower bound. So in a very recent work again with Ancana, with Christian Zillinger, and then with Roman Indergard, I think, and Dennis Kochman, who did a bit of numerics. Did a bit of numerics for us. We kind of extended this result also to a geometrically linearized analog of the Tartar square, which is this T3. Okay, this would take a bit of time to comment properly, but let's say that somehow, so this Fourier methods proved not only with this result, but also with other results that we got with Ancana later, it proved to be very somehow solid theory, at least to go to symmetrized gradient model, so to geometrically linearized elasticity. Okay, so here, okay, just sum up. So this is, we use really Fourier method. We proved this scaling law for the Tartar square. And then, okay, other related result is the one that I already commented. So we can apply also to linearize the elasticity. Also model developing a finite order of lamination. Also by being a little bit more, so taking into account also the shape of the domain, so the nucleation problems. With this, I'm finished. So I thank you for your attention.
Thanks, Antonio, for your nice talk. We already had some questions during the talk, but I think we have time for more questions.
I did not really understand what was the answer to the original question, like between flexibility and rigidity for the...
Yeah, that's a very good one. So there is no answer. So somehow...
That's a good answer. But
yeah. So somehow there are hints. So what I really didn't say is that the original answer, I didn't say anything about boundary conditions, but so the boundary conditions of that you want to put, for instance, to develop this convex integration stuff, but this is expected to be, I mean, important in the threshold regularity. So the boundary condition that you put, of course, for instance, if you put boundary condition that is inside the well, that your threshold regularity is so you are infinity, no? So I don't know. So this I'm guessing. I'm really guessing. So, but I guess that the boundary. So the boundary condition that you put. So in which I don't know. For instance, if you are in the lamination, actually this we proved. So if you are in the lamination convexal, for instance, which order of laminates is your boundary condition? For sure, it will influence the scaling and then therefore the threshold regularity, if you want. So it depends on how you phrase the question. But somehow, let's say like that. And also depends on which type of wells you are taking. But somehow, if let's say this, so this is coming a bit from here. If you remember a bit the result that I presented from Ancana, they were saying that if you have a lower bound, then the scaling, and its lower bound is somehow algebraic, then the scaling of the lower bound relates to the HS regularity of your maximum. So it's an upper bound for the HS regularity of your differential inclusion. So for instance, if you manage to find somehow so I mean if you study threshold between rigidity and flexibility for a set of wells who develops this infinite order of lamination, for instance, then you may expect somehow a lower bound of this nature, so like the lower bound of the Tartar square, and then for the lower bound of the Tartar square, then you would expect somehow a lower bound that beats every polynomial, every algebraic scaling. So this means that the upper bound for your threshold regularity will be outside every HS. So the gradient will be outside every HS Sobolev space. But this is somehow again, so this is just somehow a scaling result. So if we manage somehow to drag, for instance, and I mean, there are some ideas to drag these scaling results into models in which we have solution to the differential inclusion. So because here, this infinite order of lamination are not solution to the differential inclusion. So the differential inclusion is rigid. So if you manage to find a set, and there is as a T5, in which somehow you have solution to the differential inclusion, and you manage to prove a result that we are expecting to be of this type, then you have somehow this good threshold regularity statement. So that somehow rigid solution to the differential inclusion cannot be in any HS space. Okay, but this is not a claim. So this is kind of where we can go, in which direction we can go somehow.
Because it's kind of reminding a bit this Onsager conjecture, for the fluid stuff when you have the max integration. So I mean, I would assume something like, okay, if I know that the gradient of U is in some base of space or something, then I am rigid, and if it's below, I can construct solutions.
Yeah.
But then I don't see your answer being in that direction.
No, I mean, here there's no answer because here there is no.
Because that does not depend on the boundary conditions. The statement,
what?
The statement that you look at.
No, I mean here so in general in this type of models the scaling depends on the boundary condition. So I would guess that also the threshold regularity of this type of differential inclusion would depend on the boundary condition. This is what I would guess. But so it's yeah. I mean, and somehow if you're I mean, this one result that we have is still kind of not really the thing, but if you consider these three matrices, okay, and you take K this set, okay, then with Ancana, this also was proved also by Laurent in the discrete case. Then somehow this is the lamination convexal, okay. If you take a boundary condition here, then somehow your minimizing sequences are really this branching construction by Cohen-Mueller. And here, if you take a boundary condition here, there your energy scales like epsilon power 2/3. This is the result of Cohen-Mueller. And this corresponds to the fact that this boundary condition here is a first order laminate of K, right? So because you obtain F by a convex combination of A and B. And you have also C. But then in the lamination convexal, you have also more complicated boundary conditions. For instance, this F tilde. To obtain this F tilde, you have to laminate twice. You have to laminate between A and B. You create this. And then you laminate between this and C. So this is a second order lamination. And we proved, and also Laurent proved, that the scaling changes. It's not epsilon 2/3, it's epsilon 1/2. Okay. And so if then you relate this with the regularity, and then you relate this, I mean, with a model in which you have solutions to the differential inclusion, then somehow you would expect something in that direction. Maybe not. Maybe, I don't know, it's just the lowest regularity between these two maybe is the one that somehow. But this is nothing is really stated super clearly in this point of view. Thanks for. Are you?
Yeah, thanks.
Okay, thanks for the question.
More questions?
So you have this new. And you showed how to get the lower bound. I mean, the proof sketch. So this comes from the number of iterations you do, or how does it appear in the proof?
The nu?
Yeah.
No, the nu is kind of this problem that somehow when we reduce so when we further localize our phase indicator, we cannot really do it by just multiplying our energy by this L, because we don't have this clean Lipschitz estimate, but we have this Lipschitz estimate. So we have a constant which depends on nu, and here we have 2 times nu at the power. So here we don't have clean energy, but we have energy at power nu. And this creating this. Then the nu changes, so it's not the same nu.
All right, then I would say we thank Antonio again and all the speakers of the day.